Ladies and gentlemen, hello and welcome back once again to the briefing room. Yours truly, Eric Kavanaugh, is here for our deep dive on enterprise technology. And I can never miss an opportunity to promote Future Proof, the world's only made for TV webinar series, now in 7 markets around the country, including Silicon Valley and Washington, D.C., Fairfax County, and several other markets. Los Alamos picked us up, so that's nice. Check your local listings or hop online and look for Future Proof. Now let's go ahead and dive right in. Tackling trillions of records for real-time analysis. And yes, we're serious about that title. I think it's quite remarkable. We're going to learn about hyperscale data warehousing from a couple smart people. There's yours truly. Merv Adrian is with us from IT Market Strategy, former Gartner analyst, a legend in our industry. Always happy to have him. And Chris Gladwin, CEO and co-founder of Ocient. It's his 4th company. He knows how to build successful companies leveraging really cool technology. And speaking of that, let's talk about these NVMe SSDs. This is, of course, from PC World. Just a quick line about it. The new wave of memory-based storage blows away the older generations. And I remember a webinar that my erstwhile partner, Dr. Robin Lord, did a number of years ago, and he created a reverse pyramid. He basically pointed out at the bottom of the pyramid is hardware. And all innovation in the technology space starts at the hardware level. Then it goes up to the operating system and the apps and so on and so forth. But that hardware component can change everything. And the folks at Ocient figured that out. Now, they're not the first people to figure out that some hardware is coming down the pike and planning for it. Of course, a lot of companies do that around chip design to understand what to do. Folks who design chips will have certain partners come in and be a part of the process of understanding how they can leverage new functionality on the chips. But this was a major league game changer in lots of different ways. And that's what we're going to learn from Chris Gladwin of Ocient. And so with that, I'm going to stop sharing and allow Chris to start sharing. And folks, don't be shy. Feel free to ask questions at any point during the webinar. You can use the Q&A or the chat. Actually, I have to turn that on. And with that, Chris, take it away.
Hey, thanks, Eric. I really appreciate it. And Merv, looking forward to the conversation with you. As you mentioned, the NVMe Solid State is a big deal. And I would even argue it's kind of the biggest deal that we've seen in hardware since the beginning of computing. There have been a lot of amazing innovations in terms of technical complexity and advancement, but they've all generally been down at the hardware level in the category of making what was there before bigger, faster, cheaper. And it's been amazing because the bigger, faster, cheaper has been like 1,000,000 times bigger, faster, cheaper over the years. But solid state in particular, once you put the NVMe interface, which has become the standard right away, went from 0 to the standard across the planet, it's not a bigger, faster, cheaper thing. It's a whole different thing. And it's really the first time. And the implications are profound, which we're going to talk about in that we're in the, the 2nd inning, we were talking about baseball earlier, of a 9-inning or more game that at the end of it, the way the world stores and analyzes data is going to be very different. And that's a big deal. It's the first time it's changed. Everything else was getting incrementally better, and now it's just going to be different. So that leads us to talking about tackling trillions of records for real-time analytics. And the reason why we started by kind of focusing on this concept of trillions is trying to get to a way of putting this in terms of, a type of challenge that's a particular challenge for human beings. Kind of previous to trillion scale, when you were analyzing data or storing data, you could always kind of take a chunk of it and look at it in Excel, or you could print out the log files and just look at them. And that often was what would happen when you got stuck. Why is this thing not working the way it's supposed to? Well, let's go look at the logs and we'll figure it out. Or why is the sales data, from this part of the country looking a little wonky this week? Well, just go look at the data. One of the issues with trillion scale is that you can't just go look at the data. And one way to kind of put that in terms that makes it understandable, because trillion scale is not perceivable by human beings, is to say, well, if you were to print out 1 trillion rows in let's say a spreadsheet, it circles the earth 73 times. And if you were to scroll 2 clicks a second, assuming you could actually perceive 2 screens of data a second, which you can, but giving that generous assumption, it would still take 600 years to scroll through. You can't look at the data anymore. And so now we're moving to this realm where, as we humans use these things, we're now completely dependent upon the tools that we use, software tools, for example, visualization tools, data analytics, things like that. They're the things that are going to look at the data, not us, because it's just not possible. And, trillion scale is enormous, but, the T and terabytes, which is how much storage you have in your laptop, like there's that many bytes in there. It's this little drive sitting inside your laptop and your phone. But if you rip it out and spread the bits across the planet, they circle the earth again and again. So we're already in this realm, and we're completely dependent. No one looks at the data anymore. The other thing that's important to understand is, if you look in 2025, how many of these incomprehensibly large chunks of trillions of data are out there? Well, IDC is projecting 1.4 billion trillions of data. If you add up all that is on Earth in 2025, which is about to be next year, it's 1.4 billion of these things that are so actually 1.4 million of these things that are so big. No, what am I saying? 1.4 billion. Got my comments wrong. So 1.4 billion of these things, and each individual one of them is so big humans can't even look at them. And now we're going to have 1.4 billion of them. That's the world we're in, in 2025, and we're already basically there anyway. But that's just different. It's just not a world that we can go back like we did 20 years ago. Yeah. I'll crack open an editor and just go look at the data. No, no, you can't do that in this world. And this is the world we're in. So the good news is that there is a solution that will help us to deal with this. And this is that NVMe solid state that we were just talking about. When you're talking about having this much data, you now need to analyze it. And what really, really matters is, Eric was saying as he let us off, was if the software is perfect and your IT implementation and your data analysts are perfect, they can do things no better than the hardware. And so it really does come down to, if we got this incomprehensibly large amount of data and we got 1.4 billion of them to deal with, what we really have to have is a way to analyze this that not only can deliver the performance, but deliver the performance at a cost we can handle. Because if the answer is, well, if the amount of data that, some normal company needs to analyze can only be analyzed by $1 billion supercomputer, that's not a real good answer for just about everybody. So it's got to be realistically affordable. And it comes down to a couple key metrics that really drive this whole thing. And one is, how much does data storage cost? And a good way to measure that is, how many dollars per terabyte does it cost? And then there's, how much does data analysis cost? And they're really, when you really rip open a database or data warehouse and say, what is the thing that's limiting performance per cost? It's the number of random reads per second per dollar, which we call data bandwidth. How fast can you analyze data? What's the speed at which you can do that per dollar? These are the things that drive the whole thing. And what's happening is this profound change. So let's just start with data storage. So we've taken, on a log of cost per terabyte, how much does DRAM cost, how much does solid state cost, and how much does spinning disk cost? And what you'll see generally with spinning disk and DRAM is that these are technologies that are very mature in their Moore's law curve. Back in the 80s, when I used to work at Zenith Data Systems, and we made, we were the largest supplier of laptop PCs in the world. We were the new stuff coming, the new drives, the new memory, the new CPUs, we were on the Moore's law curve every 18 months, twice as fast. Amazing. It has not been that way lately. These charts are 2011 to 2031. That DRAM line's pretty flat, and that spinning disk line is not exactly, bending downward very fast. They're generally pretty flat. They don't get better. Meanwhile, here comes solid state. That's a new technology, hasn't been around very long. And really, before NVMe, which is the interface that operating systems and software talks to solid state. Before that existed, the solid state drives just weren't that great. They were originally, they put the SATA, with the S being serial. That's the old interface that was designed for spinning disk. It's a terrible fit for solid state. So those drives really just kind of stunk. But the new ones came out, and they didn't come out until about 4 years ago. And you can see where they are, where that Moore's law curve is for solid state. I mean, it is truly, maybe not every 18 months, but every 24 months, it's half the price for the same amount of performance, or twice the performance, same amount of price. So it is charging down this curve. And what's happening is you can see the solid yellow line is crossing under the line of spinning disk. And, that's going to happen on just an absolute per terabyte basis around 2026. That's not that far away. So literally what that means is it'll be cheaper to buy per terabyte solid state over spinning disk. And by the way, solid state right now is about 2,000 times faster. By then, it'll soon be 4,000 times faster, then 8,000 times faster. That's going to change the entire way the world stores data. Now, Ocient has developed technology we call zero copy reliability that allows us to push that curve down, basically, where we can essentially get reliability for a lot less cost. And so the net effect is, for our systems, we're already seeing it crossing under the curve. The cost of adding storage to an Ocient system with like in-memory data analysis type performance, the cost per terabyte of adding storage is already lower than the cost of S3, for example, that runs on spinning disk. So we're already seeing it. The whole world is about to see this too. This is going to completely change how data is stored. Let's talk about how data is analyzed. So traditionally, the reason why everybody had a two-tiered architecture where you have, compute is in DRAM and spinning disk is what you use storage for, is because spinning disk, as you can see in these charts, is way too slow to analyze data, but DRAM is way too slow, way too expensive to store data. So everyone had those two things in the architecture. Now, what's happening with solid state as it compares to DRAM, this is the chart on the right, it's going to drop below the cost of DRAM on an analysis basis in around 2031. I mean, in the same way that when solid state becomes cheaper than DRAM, everyone's going to use it to store data. I'm sorry, when solid state becomes cheaper than spinning disk on a per terabyte basis, everyone's going to use it to store data because it's cheaper. When solid state drops below DRAM on a cost per analysis basis, everyone's going to use it for analysis because it's cheaper. And like, those are the two main things you do with data: store and analyze it. Both of those are changing. So that's just a giant deal. And so that's the thing that enables us to deal with these, trillions of these billions of trillions of data that we have. All right, so what does Ocient do? So what Ocient does is we have made an architecture that is completely different in terms of how we store and analyze data, that's completely based on solid state. And the reason why we have done that is because there are things that architecture enables that are significantly better than all other alternative architectures. And we only focus in the areas where we know what we do will be much, much better on a price performance basis. No one cares about the 17th best data warehouse that uses that same architecture that's 50% better or 30% better. No one's going to buy that. We have to be, as a new vendor, we have to be 3 times, 5 times, 10 times or more the price performance. Otherwise, people aren't going to switch vendors, certify some new vendor. So we just focus in areas where we know that's going to be true because of our architecture. And those areas are loading and transformation. We're able to load data faster and more efficiently than alternatives. And we have some customers that are using us because the rate at which their growing amount of data they have to load is slower than how fast data is generated. So they never get there. They never catch up. And we solve that problem. Another area is real-time analytics, which is there are areas where the amount of data people need to analyze and have it be fresh, meaning there's new data pouring in and they need to analyze it within seconds. We're able to do that. And that's unique, novel. We do the same thing with data warehouse. Like if you want to do, giant joins and count distincts and crazy secondary indexes at hyperscale, we can do that. We can do that significantly better for those use cases at that scale than others. We do the same thing with machine learning. if you have a terabyte of data and you need to run regression and clustering or any of the Spark functions, something like that, you don't need us. There's 27 amazing ways to do that. If you have a petabyte of data or 10 petabytes of data, trillions or tens of trillions of data elements that you now need to go run regression on, now you need us. That's what we do. And the same thing's true with geospatial. Again, at terabyte scale, gigabyte scale, have at it. But if the analysis you need is, petabytes of data or thousands of CPU cores are just going to be kept busy all the time, that's where we come in. So that's software that we make. And our goal, which we'll talk about, is to make the software go as fast as this new solid state hardware can deliver. And that's not easy to do, but that's what we've been working on. And so go ahead, Eric. Or sorry, Merv.
No, I'm just taking.
That was the sound of my chair moving, but since you asked, so people who use Spark are going to ask the obvious question: is it the same Spark? And of course, we've talked about this. Yes, it's the same Spark. If you wrote it in Spark, it's going to run here. There's no differences. There's no proprietary version of Spark you're running here.
Right. Spark has done an amazing job of really defining the set of math functions you need to run data analytics. It's a really complete set. It's like a really good Algebra 2 book. Like, it's got all of it in there, and it details the syntax and exactly how to do it. What we do is make those things go at hyperscale. It is kind of a simple way of putting it. So it's the same math functions, same functionality, clustering, regression, k-means, and they've done a really good job. They've also done a really good job of doing all the math you can do to make those functions as parallelizable as possible, which is that's real math. And so we take advantage of all that. So that's a really good question. So our software then that we've written does these things. It runs on-prem, which I think we're going to talk a little bit about how on-prem is real and not going away and maybe getting even bigger. And then it does run on cloud. You can run on AWS or GCP or places like that, or we'll sell it as a service. So that's what we do. So let me talk a little bit then about the places where these requirements exist. In the same way that trillion scale data only exists, only machines can look at it, only machines can make it too. Humans don't type this fast. So the places where you see this kind of data is ad tech. So there's about 20 million digital auctions every second. And if you want to back test something on the last month of data, well, that's hyperscale. Financial services, if you want to analyze, let's say it's a security requirement to look at every event on your network or analyze basically all digital data for some kind of financial analysis, that's at hyperscale. Telcos, what networks do at telcos is they connect things. So if you want to keep track of all the connections and look at those connection records, like this connected to this, and analyze that for compliance reasons or security reasons or network planning reasons or whatever, they make 1 trillion rows an hour at a telco. They're a crazy scale. They really need this capability. Geospatial is another market for us with those same characteristics, operational IT and government. So let's get into the meat of what we're doing and how it's different. So there is another architecture, which we call remote object storage architectures. This has been, it's an architecture that's been around for a long time, but companies like Databricks and Snowflake and others have really demonstrated there's some really amazing value you can bring to customers with a kind of a modern version of that architecture. And what they do is they separate compute and storage across a network. That's really valuable because they can basically dynamically and elastically load data from their storage tier across the network into the compute tier, do what needs to be done, and then spin down what can be spun down. Real efficient for elastic workloads. And that's a lot of the market does that. We do something different. We do not focus on use cases that have these elastic style workloads where the active data set, which is the amount of data that's being analyzed by a typical query, fits in a compute tier. That's what they do. They're amazing. We focus on use cases where the active data set is 0.5 petabyte, 5 petabytes. Like every time you run a query, that query is going to have to look at that many things. Or there's an index, and that index is 1 petabyte or something like that. It might have 10 trillion things in it. Or there's 100 trillion data elements stuffed in a bunch of arrays, and there's tons of these arrays. The active data set is too big to fit in the compute tier. It's typically 1,000 times bigger than the compute tier. And if you had to like cache thrash that thing in and out, it's crazy slow. It's super expensive. It's not a good fit. And then we also focus on use cases where that demand is pretty continuous, maybe 8 hours a day, maybe 24 hours a day. You're just hammering away. So you don't really get the benefits of resource sharing. You're just consuming all the time. And to optimize for that, we have combined compute and storage into the same tier, into the same server. So we're physically not pulling data out of storage into compute across a network connection. We're pulling across PCI lanes. We have 400 times the data bandwidth. When you've got to physically look at data, we can look at it 400 times faster. And then when you have some kind of query that actually needs to, operate down at basically how many random reads you can get per second, we have 2,000 times more because our end storage tier is solid state. There's a spinning disk, and that's just how much faster they are. And so as a result, for these kind of hyperscale workloads with continuous complex demand, we're going to deliver things at 10 to even 1,000 times the price performance. Another interesting fact is because of this efficiency, in terms of combining into one tier, we have this zero copy reliability thing I talked about. So we don't have a lot of expansion of data to make it reliable. And other reasons, we're running on solid state, which is a lot more power efficient than running on spinning disks. They don't have little motors in them. The overall reduction in electrical power consumption is typically about 98%. That's really, really different. So that's what we do. To give you an example, what we see people doing today is if they've got some kind of hyperscale workload or use case, they'll often divide it up into different parts because no one's alternative system can handle that much. So they'll put, part of it on, and they'll have a separate ETL system. They'll have data jobs going into a different database. They'll have a real-time aggregation for some of the queries that they can, they have to have real-time load on or real-time analytics on. So they'll break it up into 3 or 4 different systems to make it work. What we're able to do, and this is an actual customer example, where we went in, we just replaced all that with one Ocient system. ETL at hyperscale is built in. Real-time analytics at hyperscale, OLAP data warehouse, geospatial, machine learning at hyperscale, all fits on one system. And the reason why we're able to do that is we have 400 times the data bandwidth. We have 2,000 times the IOPS. We can, you can handle it. It's not that we have this magical software that suddenly makes IOPS. It's our software is good at getting all the IOPS we can out of that hardware architecture that we're talking about. And we have 2,000 times as much to start with. So that's really how this happens. Another way you can look at this is just on the physical basis. This is another example with a customer that was using OpenSearch and Elastic. They had 10 racks to deliver this system that they were running, 200 nodes, also spending $40,000 on electricity. And we were able to replace that with half a rack. And, $2,000 a month on electricity. It's very different. It's not that we're doing, a slicker implementation of their approach. We're just taking a different approach. You can think of it like they're designed for the kind of the general moving stuff market. It's like a pickup truck. If you have to move a refrigerator, that's what you should use. If you're moving your child from one dorm room to another, perfect. In our case, what if you have to move a cubic mile of coal? Well, you're not going to use a pickup truck. It's a really bad idea. You're going to use a giant dump truck. And that's what we are. It's just designed for something different. How you could kind of position then this in the marketplace also relates to how it's sold. So what we've seen in the market is there's really 2 approaches generally, not just for the technical architecture, but how it's sold. One is kind of this classic sales-led growth. These are often on-prem systems. This market's been around forever, and there's companies that have been great at this for decades. And if you take the $210 billion data analytics market, according to IDC this year, about 90 billion of that is still sales-led growth, still a lot of on-prem. Doesn't get a lot of love, in terms of, I don't know. It's not one of the cool kids in school right now, but, these people have been doing amazing things, solving some really hard problems for a really long time, and they're still doing it. There are the new cool kids in school, that got a lot of investment and had amazing, profitable, outcomes with their IPOs, and like Snowflake, Databricks is about to do it. They just did a round of financing at, I think, a $42 billion valuation. Obviously, there's a big expectation of success coming there. Then you look at Google, Amazon, and Microsoft. What they've done as cloud providers is amazing. They've kind of gone from nowhere to the largest part of the market in a huge market very quickly. So that's about $120 billion in growth. Where we focus is the segment in that has these hyperscale requirements that I'm talking about. Up within the $90 billion, within the $120 billion, about $23 billion of that right now is at hyperscale. But what's happening is, as always happens every time there is an innovation or an advancement in information technology, today's hyperscale is tomorrow's large, is just normal in the future. So these crazy hyperscale things that we're talking about, there's a point in the future where that's what your phone will be doing. It'll have that much data, it'll be doing that much analysis. It's a question of when, not if. Maybe it's 15 years from now, maybe it's 20 years from now, but this is a future phone spec that we're talking about. In the shorter term, where that $23 billion is growing, it'll be $38 billion in 2027. Still a small part of the market, but giant and the fastest growing part of the market. So overall, that's what we do. And, really appreciate the opportunity to kind of share a little bit about what we're doing, hoping to have the opportunity to connect further with you and in our audience. We have a LinkedIn community and an Ocient blog and Ocient.com and all that kind of stuff. But that's a quick overview of what we're doing at Ocient.
Good stuff. Merv Adrian, step in. I'm enjoying my strange lighting scenario here with the winter sun blasting on my face. Take it away.
Yeah, I was just wondering if somebody was lighting flares off outside your window. So Chris, I guess the first question most clients ask me whenever we talk about something as potentially disruptive as this is, how is this going to integrate with the stuff I've got? So let's dig in a couple of places here. You mentioned early on, for example, you can deploy on-prem, you can deploy in the cloud. Obviously, everybody's interested in going to the cloud these days. The most recent study I have in my hand is one done in Europe for Cloudera of about 850 organizations, and 80% of them had moved more of their data to the cloud in the last year, and 92% of them planned on moving more in the next 1 to 3. But at the same time, those same people, 76% of them, said they were bringing some of it back. So people are not quite sure where to put this. So the first question is there a better way? If I'm working with Ocient, does it make more sense for me to be doing this on-prem or in the cloud? Is there's some latency, obviously, in going to the cloud? And I'm not trying to get you to sell against your cloud partners, but how does that work? If I'm a customer and I say, well, I want to use Ocient, but I want to use it on, let's say, AWS, it's the biggest. How would that work for them?
Well, we generally, when we propose a system to a customer, we propose it both ways. And really what it means is we send them 2 spreadsheets, or the spreadsheet has 2 tabs, or often it'll have 3 tabs.
Yeah.
One is, this is on-prem. So, we work with partners like HPE and Dell and Supermicro, or whoever their favorite standard hardware server is. There's a configuration line item cost, for all that hardware. And then there's our cost and support and everything. And, it sums up to a number. And, usually these are all thought of in terms of not only just what's your upfront cost for the hardware, but we generally sell as a subscription. So it'll be both upfront cost and overtime cost. And then the next tab, all right, well, if you go to Amazon, I think it's the i3EN metal node. Okay, this is the configuration of that. And these are the drives, and that's the cost per month. And it adds up, and it's got another number. And then we also will often quote it as what we call Ocient Cloud, where we'll basically run our software on, some standard servers for the customer and just sell it. The software is included with the hardware in the data center space.
And you're selling access. Yeah.
So we one of the things we get out of that is we have a very good understanding of from those customer opportunities. What are they seeing when they compare? And generally what you see is on-prem at hyperscale is typically going to be the most cost effective. And a lot of that is because the cloud providers have to have some margin and overhead of maintaining the cloud itself.
Yep.
And there's huge advantage when you're at smaller scale to just having them do it, because you're not going to have a full-time person, just running a system. And so it's more efficient to have a shared resource. you have some network connection that's not fully utilized and the servers aren't all that busy all the time. And so that generally at smaller scale, the cloud implementations are more cost effective. But up in this hyperscale realm, it works the other way, because there the servers are fully utilized, and you're not having to pay, Amazon plus their margin to have someone manage it, because when you manage it yourself. So generally, when you get into hyperscale, it will be more cost effective. Now, the argument for cloud will often be, well, we don't want to focus on the cloud stuff. We're a different kind of company. We would just want to focus on that. So even though it costs a little more, we'd rather just focus all our resources on what we do. So there's usually that strategic consideration of, it might be more cost efficient to do ourselves, but we'd rather just focus. So that's what we see. And overall, what we see is about half the market at hyperscale is cloud and about half is on-prem. It's about half and half. It was half and half when we talked to customers 5 years ago. We expect it'll be about half and half 5 years from now.
So an obvious mechanical question is, if somebody says, okay, so I'm going to deploy you and I want to do it on Amazon, do you sell hardware to Amazon that they install adjacent to those compute nodes? Have they bought them from you? Does the customer buy them from you? Who sees that part of the transaction?
Yeah. Typically, what we will do is we will specify the configuration in the form of a part number of the Amazon server they need to order, and they'll order it themselves. We wouldn't, typically they'll just order it themselves. We're in the Amazon marketplace, so anything they buy of Ocient is like, they care about that because usually they have some kind of commit and they want to burn down the commit. And so we can help them burn down the commit with our software. Then they'll just order the hardware directly from Amazon.
And we're talking about the stuff that most people don't want to think about. They went to the cloud to get away from. What does the server look like? How many units of bandwidth have I got? And
how many
all that other
drives?
stuff. They'd like not to think about that.
Yeah.
But
we'll tell them, like, this is based on their thing, their requirements. They need this much, throughput and this many concurrent queries or whatever. We'll go off and do the math and say, this is the server we'd recommend. This is how big the drive should be. Sure. And they just order it.
Now they may have other reasons for this selection that are a layer or two of abstraction up. For example, they've made some choices about the tools, the DBMSs and the analytics tools.
Yeah.
And they may already be using, let's say, Redshift or Snowflake deployed on Amazon. They want to keep using that. So you've got that part nailed. How much of this depends upon the quality of your partner relationships with those players? Do you have to spend a lot of time on getting that part right? Obviously, there's useful stuff that you do from a marketing side, but from an engineering perspective, is there a lot of work for you to bring one of these guys in to work with Ocient?
Well, the way we work with Redshift and Snowflake is there would be two different data analysis tools, each solving the problems they're best suited for. So all the refrigerator delivery on pickup trucks, that's going to be on Snowflake or Redshift.
Sure.
And honestly, we've had many times when customers have asked us if we could do that. Like, no, we're not great at that. I mean, but you should use that. You should use them for that. But then the coal, moving the cubic mile of coal, those are the workloads you put on us.
Yep.
And because we both speak standard interfaces like S3, or you can take a CTOS job out of your SQL and send it one way or the other. We've written a paper, Ocient and Snowflake, Ocient and Redshift better together. Like, here's how here's how the data flows back and forth and things like that. Then there's another set of tools that we're both using, which is a level up, like Tableau or Looker or Superset or whatever, and in each case, there's not many new vendors these days in data warehousing that have proprietary interfaces for your visualization tool. That's just a bad idea for a lot of reasons. So everybody's speaking SQL, everybody's speaking JDBC, ODBC,
and Spark,
like that, or Spark. And so, we haven't yet found a third-party tool that we can't, either like out of the box, it's fine, or we just have to do a little bit of integration testing and then we support it.
Chances are the tough love for that customer is get rid of that one.
If it was one that was that proprietary, I think everyone would be telling them to get rid of them.
When you survey customers and ask them about their analytics tools, The most typical answer from enterprises is, we know we have 5. And that sounds like a lot, but the problem is they also all say, we have no idea if that's the right number or not. And it's not. They have a lot more that they don't know about. And yeah, many of them turn out to be these little proprietary pieces that came in with some system and are still in use. And so, yeah, that's technical debt for most organizations. It's something that eventually they have to get rid of, but not now. To your point, you're targeting a different part of the market. What's your gut? I think the premise here of this presentation is, you may not think about trillions now, but you will be soon. What's your sense of the rate of entry into that level of the market in enterprises today? We know the oil and gas guys are there. We know the logistics guys are there. But how do you see this playing out over the next few years? What are your projections on the number of customers that become part of your target market?
I think most people on this call remember the first time they heard the word gigabyte, and it's this goofy sounding word.
Yeah.
And it was probably back in the day when we had learned the words megabyte, and probably kilobyte. Remember, we used to know that word.
Yep.
And then all of a sudden this word gigabyte, like, that's a goofy word, but we all learned it. And then we had to learn terabyte. That wasn't hard to learn because it kind of sounds cool, terabyte. Then petabyte, that's a weird word too. But like, basically everyone has been going through these, and these are 1,000 times bigger than each other.
That's the big thing. Yeah.
And so it's always true. I can't, there's no example of some big advancement in IT functionality, whether it's storage or networking or CPU or whatever, where the new version came out, and it's always cheaper to do the same stuff. There's no example where the way the market responded was they continued to do about the same amount of storage or networking or whatever, and they just saved the money. Like, there's no example of that.
Nope.
Every single time the market is, oh yeah, I'll do more. I'll store more. I'll network more. I'll compute more. And so hyperscale, the meaning of hyperscale will change. So today's hyperscale data analysis is something like, 1,000 CPU cores are busy all the time, is the main thing that really kind of tips into, well, you're in a different world, and the way you have to do things gets a little different. Like these advantages I'm talking about,
Sure.
Well, it's just a different world. You can't do the same thing a million times bigger all the time. Here, you just got to do a little different. And so right now, hyperscale is like 1,000 cores. You're typically analyzing half a petabyte or half a trillion rows each time you're going to query. That's like, that's today's giant hyperscale. There is no doubt that it's going to become mainstream. How fast it does that, because the thing that is enabling this at the end of the day is the NVMe Solid State Drive and the cost per storage and the cost per analysis that we were talking about earlier. That's the thing that's driving this whole thing. So the rate at which people will adopt it is going to be at the rate at which NVMe Solid State is moving the needle on these metrics.
Yeah.
And it may actually adopt it faster. And so if you look at those charts, and you can go get the roadmaps from, there's only 3 companies that make it. It's, SK Hynix, it's Kioxia, and it's Samsung. They have roadmaps. So how fast they're advancing the cost per unit of storage and the cost per unit of analysis is at least how fast the world will adopt it. And generally, it's about doubling every 24 months.
Yeah, we all love, especially analysts like me, we all love these longitudinal curves that show stuff over time.
Yeah.
And I think the key thing for customers to understand here is how, I know the word transformation or disruption gets bandied about a lot, but this really is a knee in the curve. It is, we're starting a different curve. If you think about fundamental revolutions in business. The Industrial Revolution not only made stuff we were already doing easier to do, but it enabled a whole bunch of things we couldn't do before. Build buildings taller or transport things across the country while they remain fresh enough to consume. The computing stuff we've done for the last 50 years, and I've been here for most of it, was about doing what we were already doing, a little better, a little faster.
Right.
We're talking now, and I think you nailed it with your analogy. This data is too big for people to look at. it needs a fundamentally different approach to how do we work with this data and what are we going to do with it. And what we're going to do with it is things that we never could have conceived before when we were limited by what we were able to look at.
Right.
So the real-time analytics stuff you're talking about, the kind of modeling you have to do in real time for a large-scale logistics systems moving product from multiple places to multiple places, we start tackling problems we couldn't do before. And so it's very exciting to think about what else are companies going to do with this? What else are users? Do you have any interesting ones you're allowed to talk about? I know some of your work is government, but any intriguing use cases that you're seeing these days?
Well, I think this is a really interesting topic because this idea of disruption, and I'm using the word from The Innovator's Dilemma, which really, that book by Clayton Christensen really, really analyzed this in detail. Disruptive technology innovation is where the advancement is so significant, and typically 10 times or more.
At least in order of
that the market that develops is primarily only enabled by the advancement. It can't exist before. So like at my prior company, CleverSafe, we did on-prem hyperscale data storage software, very similar. And the markets that emerged for that were things like genomics data storage, photo sharing systems, cloud storage providers, things like that. None of those existed when CleverSafe started, because they couldn't. During the 10 years we did that, we improved the price performance of reliable storage by about 100 times. And I can tell you that whoever you use for your cloud, and they charge you like, I don't know, $2 a month to store it forever, they can only do that because the price to them is 1/100th what it was. If it was $50 a month, they're not going to be able to do that. So the challenge then for us, when you have one of these disruptive things, is a lot of it initially will be, bigger, faster, cheaper, what's there. But most of it, probably more than 80% of what's going to happen, how people are going to use this 10 years from now, can't exist today. It's like an elevator company. Like you invent the elevator, there's no building under construction that needs an elevator because you can't have a 10-story building without an elevator, So and like all the ways, the types of buildings that use elevators, none of them were in construction when you launched the elevator version 1. And you have the same issue here. And so what are some of the interesting things that we can do? So one of the interesting things, without too much detail, it's not a classified system, but still is there are organizations that are looking at storing network metadata on a very large scale and analyzing it. And things that would have cost, billions of dollars now cost millions of dollars to do for that kind of analysis. And, I'll give you an example, capacity planning for 5G. 5G is the largest capital expenditure in human history. It's about $7 or $8 trillion. Okay. That's real money.
Yeah.
If you're a telco, you need to know things like, what does demand look like on my network? How does my network perform today? Because I need to know that if I'm going to be spending all this money. To really know that, you have to have full resolution network metadata on every connection your network makes, because that's what networks do, and how they performed and when and where and why and what. Like up until now, that's not feasible. I mean, you would need a supercomputer. So now we go to telcos and we say, for single-digit millions of dollars, you can collect and store and analyze all that. That's super different than what they've been able to do.
A game changer for sure. Yeah, absolutely. And then, there's the structured versus unstructured. So much of this new data that we're talking about, to your point, it can't comfortably be shoehorned into an old DBMS. They're just not equipped to scale. And even if you could get it in there, the likelihood that you could get it out in any sort of a timely way is just, they're not designed for that sort of work. At least a third of companies say they are not using their unstructured data effectively. So, how do you guys think about this? Basically, you're putting the bits on disk, and we've got Spark, we've got some tools, but do you see anything in your architecture or with the partners you're already working with that is going to make it simpler for people to work with data that they haven't got good descriptions, good metadata, good governance for. That feels like one of the big problems people are grappling with right now. How am I going to get my arms around this new stuff?
I would say there's some kind of theorem somewhere, I think, in data. Like, data never starts in a form that is usable.
Fair enough.
Data is always a mess in terms of like how you want it to be. Oh, it's in relational schema, it's indexed, it's compressed, it's encrypted, it's ready to go.
Yep.
It never starts that way. So, and it, even unstructured data has actionable structured data in it. You just got to get it out.
Yeah.
And so what we're seeing more and more, particularly exaggerated in this hyperscale domain, is the analysis of data is one set of challenges, but the getting data analyzable is a whole other set of challenges. And we see this, for example, in machine learning. If you feed a large language model some not very well structured data, and then it's going to be like it's like it's been taught by teachers who didn't know the subject. And as a result, it's going to just not make any sense. So you have to feed it data that is like correctly cataloged and correctly, sorted and all that stuff. Well, to do that on trillions of things, in data, it's never static, by the way. So trillions of things are coming in every day.
And they're not the same as yesterday's were.
Yeah. So now you got to get it to where a large language model or some other process, an OLAP database or something can use it. Well, that's a challenge in itself. So that's the insight that we're seeing is, in some cases, the getting data into an actionable state, which is a never-ending thing, is actually harder and more hyperscale than the actual analysis. So so that's really where we're seeing an opportunity to add some value. And it is, and there's no end in sight, because the amount of data, I guess, another kind of rule that we have challenged people on many times, and so far no one has come up with a counterexample, is that every new technology makes more data than the prior version. And so far no one's come up with an example where like version 7 of the plane, the car, the building, the phone, the microscope, the whatever makes less data. Just like they always make more. And so that's what's creating this never-ending flow of data that just keeps getting bigger. And that always has some kind of semi-structured, it's never fully structured the way you want. And that makes this increasing challenge to prepare data for analysis at hyperscale.
And it complicates the trust problem. I mean, this is something that we hear time and time again, is I don't know if I can trust this analysis or even this data. And regulatory bodies, who always lag technology by a decade or two, are already asking, how do you explain what that AI system came up with? And most organizations don't have good explain capabilities inside the black boxes they're deploying, which ought to be a flag. It's fascinating to see that some of the experiments, I was just out at IBM's Yorktown lab, and they were talking about some of the stuff they're doing, where they were showing how they're building models that are designed to create regulatory reports in the formats the regulators expect them to be.
Right.
And that's not a trivial challenge. So we're going to grapple, I think, with this problem for some time, and bandwidth of getting that data back to whatever it is we build is going to be on the critical path. So I think you're very well positioned. What's next? From a high level perspective, what's the roadmap for you guys? Next version, next product, perhaps in the family. What are you thinking?
Well, there's pretty cool announcements coming up. Our version 23, I believe, is about to be announced. Just gives you a sense of how long of a journey it is when you're on version 23. That's major releases. There's a bunch of smaller ones, but there's some really cool core technology as it relates to searching. And this kind of gets back to what you were saying about structured versus unstructured data. The ways you deal with the reality that just data is never in a state that's easily analyzed to start. well, not never, but it's often not in a state that you need it to be to analyze it. Let's just put it that way.
Yep.
And so then you create there's all these technologies that people have made over the decades, how you deal with that, things like indexes and stuff like that. So we have some really cool new indexing technology that we're bringing out. It's the kind of stuff that, it'll be fun to explain, but it is really actually complicated in terms of like what it's physically doing to basically take just unimaginably, as we were saying earlier, imperceivable amounts of data, and allow you to do things like, search for things in it. And the way it does it, this goes back to this whole idea of like how big this data is. A lot of times when you hit the return on a query on, let's say, 50 trillion things, it's kind of interesting to see like, well, how's that actually doing that? Like if it gives you an answer in 6 seconds on 50 trillion things, like, what did it do? And, I mean, when you break it down, like how many parallel tasks, what was the IO layer doing? How did the optimizer do this? Maybe there was some kind of funky index that, helped this whole thing go. But anyways, so you're going to see some stuff where like just the plumbing of how some of this is happening is really pretty cool.
Yeah, some of this is happening down in the less highly scaled data world.
Yeah.
With things like open table formats, so that you've got some layer of metadata over the raw store that has some of the more commonly used statistics, so you don't have to go all the way down and read through it. I think we're seeing much more of that happening. What's your prospect for 24 in terms of your expectation for customer adoption? How are you doing? Are you keeping up with the number of customers you got? Is it a strain?
It's a strain, but in that the limiting factor for how fast we can grow is a function of how many resources we apply. Mm-hmm. It takes time and effort to identify customers, to understand what they need, to assess whether or not we're a good fit. We definitely have to do that right up front, but it does take some work. Work with them to figure out like how best, because we deal with this stuff on the inside of our software, but there's a lot of things on the outside of our software that are in the customer's domain, like which higher level tools are you going to use and how's it going to interface with this data source and all that stuff. So it does take a lot of work, and that's really our limiting factor, in that we can, we also can't just like throw this across the wall to the customer and say, good luck with that. And because we need all of our customers to be really successful. We're still a relatively new company. And the way it works is if some of these initial customers don't get amazing results, everyone's going to know. Like in these hyperscale markets within a vertical market, like everybody knows everybody. Sure. So if you go into one of them and like your campaign forecasting system in ad tech doesn't work quite right, everyone's going to know in that market. But on the other hand, if it really delivers amazing, everyone's going to know too. So we have to focus on that. So our limiting factor really is people, and we have to be very careful to only work with customers that we know we can do amazing things for, because there's a lot of times technology companies will take on customers that aren't a great fit because they want the extra revenue or whatever. And, there's some companies that can do that. We're not one of them. We can only, it all has to be working amazing.
Well, so much of what your best prospects do is very bespoke, right? They're writing their own code, they're writing their own tools. And so to test it with you is something that, you've got to get very deeply involved in early to ensure the likelihood of success. I see Eric has rejoined. I'm wondering if you had a question you wanted to bring up. So I'll
Chris,
step back a minute.
Yeah, if you would go back to one of these architectural slides where you talk about Casa versus Rosa, I just wanted to show that again and kind of point out, you referenced you're on version 23 that's coming out soon. And I just want the audience to kind of appreciate something. I'll create an analogy too. I spent a lot of time studying SAP, and of course, Hasso, very, very interesting character, something like 20 odd years ago, I think longer than that, in fact. he realized that RAM would be less expensive or comparable, at least with spinning disk. And that's why he set that in giant behemoth of SAP on the path towards what is now S4 HANA, SAP S4 HANA, all in memory. And you had the same sort of observation, the same sort of realization, and you did something similar in that you realized, hey, this is going to be a completely different architecture. We have to rebuild this thing from the ground up. So that's why you're on version 23 coming up, because you had to rewrite everything. And it reminds me of a quote I may have used in that radio show I did with you, Dr. Michael Stonebreaker, of course, the godfather of the modern database on DM radio, probably 10, 12 years ago. He said, 80% of the code that has been written should just be thrown away. And his point was that it was written for old architectures. And so the old operating systems have different demands. And it really does take that thorough of a rewrite, kind of like Teradata talked about throwing $250 million to refactor their whole stack they run on the cloud. That's a huge undertaking. And you saw that coming. Could you just talk about that for a minute?
Yeah, it goes back to kind of what we were saying, like how things get done. If the way that a spinning disk works is there's a read-write head and it's in one physical location. It's either sucking or spinning bits. And if you want to move it to another location, you physically have to move. It's like moving the needle on the record, settles in the track, and then the platter, the record, has to spin around to the beginning of the track so you can start reading or writing again.
I used to write code to do that in COBOL. Yeah.
The amount of time that takes to move it and start writing hasn't changed in 50 years because it's a physical thing. And so as a result, all the kind of prior generation of databases that were architected for spinning disk as the storage did amazing technical work to deal with the fact that your data query wants to do a whole bunch of things at once, but the read-write head is going to do one thing at a time. So they do really sophisticated stuff to make that work. Solid state is exactly the opposite. The current, like the new generation of solid state drives, do 1,000 things at once. That's one of the ways they get so much performance. It's not one at a time, it's 1,000 at a time. That means your whole IO layer, which is 40% of the database that deals with all that IO, input and output into your storage tier.
Right.
You got to rewrite that from scratch. You can't just say, I'll take the old one. Well, you actually can run one of those architectures on solid state. It'll run 10 times faster than spinning disk, but the solid state runs 2,000 times faster. So to get that, though, you got to rewrite the whole IO layer. That's 40%. Now you go up to your optimizer, the thing that figures out how you run the query. Well, it needs to know that I can do 1,000 things at a time per drive in order to make the right choices on how to do the query. There's always an infinite or effectively infinite number of ways to run the query. Do you do the sort first? Do you do the shuffle first? Well, if it doesn't know that, like, how different the IO layer is, it's not going to be any better. So you got to rewrite that. That's another 40%. And next thing you know, you're like, this is Ocient. Next thing you know, you're down in the memory allocators in Linux and rewriting those because they can't flow bits around fast enough. So that's really what you have to do. It took us about 300 person years to do.
Wow.
I mean, that's the price of poker. And it's not that we're like, oh, we're so much smarter than everybody else, and that's why it's so much faster. Like, no, they just solved a different problem. And they're great at solving their problem. We're great at solving our problem. It's just different. But yeah, it is one of those things when you 1000x or more your underlying core capabilities that the hardware is delivering to you, and they deliver to you in the exact opposite interface, parallel versus serial, that it used to deliver to you. Yeah, you're going to have to rewrite your whole stack.
Yeah, and the perennial issue is always about supporting the past. So, Eric, your examples, SAP did a rewrite, but they still had to support everything they were already doing. Same for Teradata. I like to tell people, you don't want to have to saddle your horse in order to start your speedboat. Just because that's the way we built it back then.
Wow.
Can we eliminate that 80% of the code path that we were talking about? Yeah, absolutely. I don't need to process that stuff anymore. I'm not doing it that way. I'm not even doing the same set of tasks. So that's the opportunity you guys have seized, and it's really exciting. It's good to hear about it.
Yeah, well, you've targeted these very large, very complex environments. So you're talking life sciences, I'm guessing. You mentioned government. or just IT operations for very large companies that get incredibly complex. Telco is an excellent example where you've got to be able to leverage all of this data. And what you're doing is you're changing the day-to-day activity of the analysts and of the business people, right? I mean, that's the goal, is to change what you're doing. And I remember years ago when in Adobe Photoshop, you didn't understand how big the file size was. You want to run a filter, you hit enter and then watch the slider bar for 6 hours. And that's a very painful experience. And so you've evaporated that wait time. And so now people are changing what they do every day who are using this technology, right, Chris?
Yeah, I mean, essentially, in a very high level, you're taking the performance that used to be only in in-memory databases and bringing it to kind of the hyperscale world using the lowest
and data that isn't in
cost
databases.
Yeah,
at least as important.
Yeah.
And a landing zone for all of this streaming data, because that was the real challenge with Kafka and Pulsar and Flink and these other technologies. Is okay, if you're going to have screeching data heading towards my organization, I need some place to land that stuff. I need runways to be able to absorb that information. And that's what you've created here as well, right?
Yeah, I'll make, I guess, a good kind of summary comment is what we were a part of doing at CleverSafe was changing the way people store data. They used to store some of their data and delete the rest of it, because that's all they could afford to do. And there was a lot of tools about like what data to get rid of and how long you retain it. And by and large, the world has gone to a model where because storage is so cost effective, they just store everything. They don't like, when's the last time that you went through your like picture files and just deleted stuff? We used to remember 360K floppy disk. I remember you'd be like, man, I got 360K. I can delete that. That's 8K. I can delete, like we don't do that anymore. Like you just, like it's all there, archived to forever. The same thing is about to happen to analyzing data. The reason why we analyze just little parts of data is because it's too expensive to analyze it all. Well, what if it wasn't too expensive to analyze it all? Well, then we do it. Well, that's about to happen. So like one of the use cases that we're working on is network security. Today, enterprises will typically have some kind of real-time tool that looks at like stuff, the email flying by and the network connection attempts and point out problems and say, oh, that's a threat, I'm going to block that or whatever. Well, that's still going to happen. But what we see happening is, and in addition to that, they're just going to store all the network metadata and all the metadata for all their critical servers. Like if it's a bank, anything that touches money, anytime there's a file open, a USB connection, whatever, just log all that. And then everything on the network, like anytime the network connects to anything, I'll just log all that, and it's going to be this giant log file. Well, if that log file doesn't cost that much, and then what they're going to do is you're just going to run regression to forever, where you're just going to have Spark-like jobs that are just looking and like, tell me everything that's 4 standard deviations above normal, login attempts, file opens, whatever, just all the time, just thinking, going. And then it's going to say, hey, that's a problem. Well, if that cost $1 billion, which it previously did to do that, no one's doing it. Okay, let's say that costs $1 million. Well, that's, if you're a big financial services company and the next time you get a ransomware call or there's some, federal, compliance thing, and you're going to go back and you're like, well, let me know what happened. I have a Wayback Machine for my network and my servers and everything. And I'll just go see, I'll just know if some virus has gotten into my company, like I'll go back and look, like, where'd it go? What files did it take? What did it do? I can go look. So like, that's an example. Like that's like cloud storage is a perfect example. Like we just store everything because it's so cheap. Well, we didn't used to store everything. Well, now we're about to analyze everything because it's about to be that cheap. And really this NVMe solid state, this is the thing at the end of the day that's enabling it. And, Ocient's, look, we're not the first, we're not the only, maybe we're the first people to do this hyperscale thing on solid state, but like all the data and analytics is going to solid state. I mean, it's just going to happen. And then when that happens, the world's just going to analyze everything.
Wow. That's a great way to end this show, folks. If you have any questions, feel free to reach out to me, info@insideanalysis.com. .com comes straight to me. Thank you so much, Merv Adrian, for joining us. Thank you, Chris Ocient,
Thanks,
as
guys.
always, for a wonderful presentation. I think this stuff is just fascinating, and it's amazing. And like you say, everything is going to solid state. So get ready, strap on your seatbelts. We're going to be rocking and rolling. We do archive all these webinars for later viewing, so share it with your pals at work. And with that, we'll bid you farewell, folks. You've been listening to The Briefing Room.